Remember, we started down this path because we want a grown-up version of strain. Graduate school version of strain. So let's set out to do that, right? Remember, I drew two potatoes. Initially, the first thing I drew in this class, and we have a little line segment DS, and then undergo some deformation, and then we have D little s, right? And you know the difference between like ds and dx is that x is a vector, s is just the magnitude of that vector, right? Because what is a strain? A strain is a change in length of something, right? The change in length of a line segment, of the line segment. The change in length of a line segment normalized by something, right? That's what strain is. And so, so what we're going to do is look at, well, let's just look at what is ds. All right, so ds, and I'm talking about little s here, is equal to the magnitude of the vector dx, right? What is the magnitude of a vector? Well, the magnitude of a vector is the square root of the sum of the squares of the components. Right? Everybody agree with that? Remember that? Magnitude of a vector is the square root of the sum of the squares of the components. All right? So, I don't want to deal with that square root. I don't want to carry that square root of sign around everywhere. So I'm going to square both sides of the equation, right? So if I square both sides of the equation, I can get rid of that square root sign, right? So then I just have, this, you know, ds squared is equal to dx1 squared plus dx2 squared plus dx3 squared. And that, another way to write that would be to write the vector, the dx, or write it in vector notation. All right, remember I said by default, whenever I write a vector, it's a column vector. So that means this is dx, what is that? Dx transpose, right? So this thing is equal to dx transpose times dx. Okay, so I'll just rewrite that here. We have ds squared is equal to dx transpose dx. This is also just a dot product operation. All right. So using the same exact arguments, we can write that d big S squared is equal to this writing app doesn't have a good wrist. Sometimes when I touch it with my hand, it jumps around. Right? So ds squared is d little x transpose d times dx, and d big S squared is d big X transpose times dx. All right? So what we want to look at is we're going to look at what is the difference in those two. So what is the difference between d little s squared, d big S squared, right? That'll give us some measure of a change in length, right? And so then I'm just going to write out, make these substitutions. So d little x transpose d little x minus d big X transpose dx. Okay, but we have an equation that relates d little x to d big X, right? What is it? d little x equals the deformation gradient times dx, right? Remember, that's what the deformation gradient does. The deformation gradient takes vectors in the current configuration, the reference configuration, and maps them into the current configuration, right? So let's make that substitution. So again, d little x transpose dx minus, here's the substitution, f times d little x. I'm sorry. I made the substitution. I wrote it in the wrong place. Sorry. Do it here. D little x is f times dx. And then this whole thing is transposed because of the transpose there. And then we have f times dx minus dx transpose dx. Okay. Now, whenever you have a transpose operation, if you have the multiplication of two terms and then it's transposed, does anybody know what how that works out? If you want to distribute the transpose, what do you do? Yeah, so you distribute the transpose and you swap the order, right? So I get d big X transpose f transpose times f times dx minus dx transpose. And what I'm going to do here is I'm going to stick an identity matrix there times dx. The identity matrix doesn't do anything, right? dx times the identity matrix is dx. Right. I'm going to just make sure I've got my vector symbols here. Right? But when I write it like that, then you can clearly see I can factor out the dx's, right, of this equation. So then I have dx transpose times f transpose f minus I times dx. And what we're going to do is we are going to call this thing, by definition, we're going to define it to be 2 times E. And the 2 will be made clear later why that is. Right? And so then with that, I have that E is equal to 1/2 F transpose F minus I. And this thing we call the Lagrangian strain, or sometimes you'll also see it as the green St. Venant strain. Again, just named after two guys. I think Green defined it in 1841 and St. Venant in like 1849. Of course, information didn't travel as fast back then, so they independently did it, but they didn't know about it until much later, right? So, and again, we call it the Lagrangian strain. Remember, another name for the reference configuration is the Lagrangian configuration. And so we call it the Lagrangian configuration is because we're referencing it back to vectors in the reference configuration. So basically the Lagrangian strain is defined in the reference configuration, right? So if I take these two vectors, multiply it by that strain, then I get the length, the change in length in the reference configuration, like with respect to the reference configuration. Okay, and again, the two will be clear later. Okay. So, remember, F is I plus grad U transpose. So then F transpose is equal to I plus grad U so we're going to plug those back into our definition of strain for F and F transpose. We'll have that E is equal to 1/2 grad U plus grad U transpose. And again, I'm trying to be explicit by putting the big X. Remember, big X always has the bars on the top and bottom. So I'm saying that's the gradient with respect to big X of U, right? Plus or in additional notation, this is partial UI partial big X J plus partial uj partial big X I plus So, so now if we were to linearize, so this, you see this is nonlinear, right? It has this nonlinear term here, okay? So, if you have small u, or specifically small gradient of u, displacement gradient, and I'll talk about what small is in a second. If you have small u, then perhaps this could be ignored. And in that case, then you have the notion of the linearized strain or the small strain, and that's grad U plus grad U transpose. Or in additional notation, 1/2 partial UI partial XJ plus partial UJ partial XI. And so, remember it was, when we defined it, we said 2E, right? Which ultimately, when you solve for E, leads to the 1/2 out front. And then the linearization, you still have the 1/2 there. And so, who recognizes this? I mean, I even show this when I teach undergraduate geomechanics, right? This is the small strain or linear strain, or what is often, just in your first, introduction to strain, this is the strain that you're introduced to. And the reason it has the 1/2 out front, as we'll see actually in next class, is because there's a geometric interpretation, right? You can basically you can just draw a cube and look at how it deforms, and you'll see that there's a 1/2 out front due to the geometric interpretation for small strain. So because of that, when we define the large strain, the finite strain, the Lagrangian strain, we put the 2 there so that it has a consistent definition with the small strain, or the linearized strain. Right? That's where the 2 comes from. Right? So this is the, we call this the linear strain. We call also sometimes this is known as the Cauchy strain. Okay, so then what's small? Small we define as whenever small is whenever the magnitude of the gradient of u is much, much less than 1, right? One definition of the magnitude of a second order tensor A would be the tensor contraction Aij, right? So this is a second order tensor. Again, we have 2 repeated indices, so we're going to sum over I, sum over j. This is going to be a scalar. We call that the magnitude of the tensor. So whenever the magnitude of the displacement gradient is much, much less than 1, that's when we call small, and that's when you would refer or could get away with using the small strain. Now, often we talk about what we're deriving these nonlinear strain measures. We talk about finite deformation continuum mechanics, right? And so what I mean by that is, for example, imagine a really long, slender bar, right? And then say we're going to load the bar transverse, which is going to cause it to deform like this, right? In this case, if you looked at the axial strain in the bar, because it's so long and slender, the strain would be small in the bar, very small. But the deformation can be large, right? And in this case, if you have large deformation, even in the case of small strain, this small strain, Cauchy strain, will not be valid. And I'll show you an example of that in the next class, right? When we look at the geometric interpretation. But basically, the reason is those nonlinear terms account for rotations, and when we zero them out, then we don't account for rotations. And so what you'll see is you can have a pure rotation, meaning you can have no strain. If you simply just rotate a member, this strain will change. That strain will remain constant. Like if you're just rotating something, you're not straining it, right? You're just rotating it. There's no strain. This strain will remain a constant value, or 0 if it starts as 0, whereas this strain will change with a rotation. So what's an example where you could have small strains and large rotations in subsurface problems? Horizontal wells, right? We don't break the drill pipe but we bend it 90 degrees over a very large radius, right? So yeah, in that case, in the case of a drill pipe, you can have very small strains, but you can have large rotations, which would lead you to need to use a large strain or finite strain, finite deformation formulation.